Welcome to the second part of Lesson 3.3, a guided exercise on how to solve a spatial or geographical problem. In this lesson, you will solve a problem-based guided exercise. The exercise is inspired by the scientific paper Communities, Landscapes, and Interaction in Neolithic Greece. You can find an interview with one of the co-authors, Markos Katsanis, giving the context of this work in the previous lesson, Lesson 3.3 Part 1. You will work with data from Karystos, Euboea, Greece. For security reasons, the actual archaeological sites are not accurate but close enough to give a real impression. The question for you to answer is, where should an archaeologist search for more prehistoric remains in the area of Karystos? The 5 basic steps and procedures to solve a geographical or spatial problem are implemented in this exercise. If you need a reminder on the steps and the basic geoprocessing tools, you can explore Lesson 3.2. The first step to solving the problem is understanding the assignment and collecting literature on the issue. Following is the procedure to collect and organize the data. The data can be text, photographs, maps, videos, audio, questionnaires, GPS data, field observations, and many more. The most critical tasks for solving a spatial problem are the organization of the data, the creation of spatial databases to store and manage them, and the carefully reported metadata. In this case, you will use the data provided in Lab 3.3. It should be saved in C, MOOC MINERVA, Module 3, Lesson 3.3, Lab 3.3, Raw Data, Karystos Greek Grid. You can open by double-click lab_33.qgz, stored in C, MOOC MINERVA, Module 3, Lesson 3.3, Lab 3.3. Before starting the guided exercise, you can stop this video to explore the data, open the attribute tables of the layers, and try out the tools shown in the Lesson 3.2. To predict the areas where is most probable to find prehistoric remains in the area of Karystos, 2 sets of criteria should be met. The hydrological criterion is the first one. Areas near water resources, and specifically areas located 1,000 meters from springs, and 1,500 meters form ravines. The second criterion is related to the geology. Areas of alluvial deposits and areas of scree and talus cones should be excluded, since is very unlikely to meet prehistoric remains in such soils. To design the workflow is essential to translate the criteria to 3 kinds of zones. The first refers to areas of influence or effect, meaning areas where the phenomenon is likely to happen or to be affected. The second refers to areas of exclusion, which they are areas that should be removed from our analysis since the phenomenon is unlikely to happen there or is prohibited from being included. The third and final refers to probable or predictable areas, meaning the output from the previous synthesis. It can be the final zones or the most probable. In some cases, a ranking is included in this step to make a final choice. In the following slide, the appropriate workflow for this case is explained. The first criterion is to be near water resources. A zone representing the water influence is created by a combination of 2 areas. The first area refers to a buffer zone of 1,000 meters around springs. The spring's input layer has point geometry. The output of the buffer tool is always a polygon geometry. The other area is a buffer of 1,500 meters around the polyline layer of ravines is necessary. The final area of the first criterion is the union of the 2 buffer outputs. The second criterion is based on the geology layer. Develop a zone of exclusion consisting of soils unlikely to hold prehistorical remains. One of the pathways to solve this is to select by attributes from the geology layer the soils that are described as alluvial deposits and those of scree and talus cones, then save as a new layer to be used in the next step. The last step to create the most probable areas is to erase from the zone of water influence the zone of exclusion. You can use the tool difference, but you can find at least 2 more ways to solve this problem. Through spatial analysis, information is created from data. Of course, other pathways of geoprocessing tools can solve this problem. It is rare to have a unique solution. Explore and check your results and try other ways to create the same output. The final step is the visualization of the results, which will be presented in the next module. If you are a beginner or need some help, you can click the demo video to follow step by step the workflow. This is the end of lesson 3.3. Thank you for your attention.